The objective of this video is to develop the current linkage approach to calculating air gap fields, and specifically we're going to be talking about the normal components of air gap fields, that is, the radial components of the field in the air gap of our machine. This is an alternate approach to magnetic equivalent circuits. It can be used in combination with magnetic equivalent circuits, and it really is actually a direct solution to the Maxwell equations, but using the simplifying assumptions that we've been working with so far. So assuming infinite permeability in our steel and that our air gap fields do not vary with the length in the air gap, that they're uniform as we traverse the air gap. And this approach is less detailed than magnetic equivalent circuits. You're not so worried about you're in fact only worried about the radial component of your fields. You're not concerned with tangential components. And you're assuming that your back iron of your steel has infinite permeability. So whereas the magnetic equivalent circuits allowed us to place flux tubes and reluctance elements with finite permeabilities, this approach only takes into account the permeability of the air gap. This is a tool for studying motor windings. It allows us to develop a single coil of an electric machine as a fundamental building block, and then assemble those coils into complete windings to quickly calculate the total field in our motor's air gap. And it also is a graphical approach. We can draw diagrams to understand what's going on. And so you'll see that as we develop this video. This builds off of the idea of an equivalent surface current density, or a point or a line current in the air gap. So we'll consider our stator as this slotless structure with distinct points where we have current coming in and out of the page, and those points are located at the center of a slot opening, which we talked about in a previous video. So we're going to start by sketching a slotless stator with a single coil, and the coil again has two sides, so one side going into the page, one side coming out, and we're going to calculate the H field in our air gap. And in drawing this, we've made the following assumptions. We've assumed that we have a coil with two sides, and each side consists of ZQ inductors. That is, the coil has ZQ turns. At the angle location alpha 2, we have ZQ conductors going into the page, each carrying a current of I. At angle alpha 1, we have ZQ conductors coming out of the page, each carrying a current of I. And we've labeled the center of our coil, that is the average of alpha 1 and alpha 2, as being alpha C. And then we've assumed that we have a constant air gap length delta. That means that the air gap length doesn't vary as a function of alpha. No matter where we are in the stator, we can be over here, and we can cross the rotor, or over here, or over here. No matter where we are in the stator or the rotor, we have the same air gap length between the stator and the rotor. We can take this diagram and we can sketch a diagram of what our stator looks like if we were to unroll it. So starting at alpha equals 0, which is this axis here, and then working our way this way, counterclockwise around the air gap, we're going to draw where the conductors are located. And furthermore, we're going to define the angle between the conductors, or the coil span. We're going to define it as gamma. And then we'll define the angle outside of our coil as beta, so that gamma plus beta equals 2 pi. Okay, so we've made this sketch, and this diagram on the right is going to be more useful later on. We're just trying to show you that you can unroll your stator and draw it as an equivalent linear representation, which makes drawing things a little bit more convenient. It's easier to draw in straight lines instead of arcs. Our task is to calculate the total H field in the radial direction at any location in the air gap, and we'll do this by imposing Maxwell's equations. Specifically, we'll be imposing Ampere's law and the law that the divergence of B is equal to 0, the fact that we have no magnetic monopoles. We can write Ampere's law in terms of our H field with our circumferential current density, or our surface current density. And we're going to be evaluating Ampere's law over an Amperean loop that spans our air gap. In fact, we're going to be considering a few different Amperean loops. In all the loops, we're going to be crossing our air gap between the conductors. We'll say somewhere over here. And then we'll either be wrapping all the way around to the other side of this conductor. And again, it doesn't really matter how far we go. We could cross the air gap over here, or over here, or over here. It doesn't matter because we're not encompassing any further conductors. As long as we don't cross the air gap all the way over here, all the points will be equal. Because our H field is 0 in the iron, because of that equipotential assumption. So Amperean loop 1 is we go out in the center of the conductors and we come back on the other side. And our second Amperean loop is that we again cross in the center of the conductors, but now this time we return also within the conductors. And we'll call this loop A and loop B. And remember that we're assuming that the H field does not vary with the air gap length, so when we evaluate this integral, we can pull H outside as long as we multiply by the air gap length. You'll see that I've written this equation as being evaluated at location alpha c. That's because we're assuming that this first loop in the center of our air gap is located at the coil center, alpha c. It can be anything that's between these two conductors. But for convenience, we've already labeled alpha c, so we'll call it alpha c that we're evaluating the first part of our Amperean loop on. And then we're going to return somewhere else. That's at location alpha. And so when we set up our line integral for our current, it looks like this. And the alpha prime business is just setting up an integration variable, just mathematical notation. So we have two cases to consider based on where alpha is. Is alpha in this region here? That's case 2. And case 1 is if alpha is out here somewhere. So loop A versus loop B. Loop A corresponds to if alpha is out here somewhere, and loop B corresponds to if alpha is in here within the conductor, within the coil. So in case 1, when alpha is in this region out here, we take this Amperean loop, and clearly we're enclosing a current density of ZQ. We're enclosing a total current of ZQI. So our integral evaluates as such, and if we plug this into this expression up here, we can get an expression for Hn. In our second case, now we're going to be considering this Amperean loop here, where we stay within the coil. And clearly when we take this path where we stay within our coil, we don't enclose any ampere turns of current. So great, we now have expressions for Hn of alpha, but we haven't truly solved it because we don't know what Hn of alpha c is. We can relate Hn of alpha to Hn of alpha c, but we don't actually know what Hn of alpha c is. In order to resolve this, we need to impose another Maxwell equation, which is that the divergence of B is equal to 0. So we started by imposing Ampere's law, and now we'll impose the fact that there's no magnetic monopoles. And for our purposes, we want to express this in the integral form, which is that the integral of H over all surfaces needs to be equal to 0. We can't have any net source of flux. You have to have flux in closed paths. And we'll conveniently decide to do this over a cylinder in the air gap that encompasses our rotor. So we're going to place a cylinder over our rotor and impose that the surface integral of H dot ds over all surfaces must be equal to 0. And when we evaluate this surface integral over this closed body, we can neglect the axial faces of our cylinder because we're assuming that there's no axial fields. We assume that our fields only have the radial and tangential components. And in our case, we're not even worried about the tangential components. We're strictly worried about the radial components because we're doing a surface integral over a cylinder. So we can set up this integral. And now what we're going to do is we're going to go back to our expressions that we've underlined in blue above. That's these expressions for our H field at different parts of our air gap. And remember, these are broken down based on the value of alpha, whether or not alpha was within the span of the coil or if it was outside the span of the coil. And since we've got these conditions on alpha that span one complete revolution from our coil to outside, that encompasses a full 0 to 2 pi. So we'll start with our first condition here. We'll start with the case that alpha 1 is less than alpha, which is less than alpha 2 plus 2 pi. So that means that we're taking the Amperian loop that returns somewhere in this region. And then we'll integrate our second case. And so for our first integral, we're simply going to plug in this expression for hn of alpha. And remember that in our second case, we're just always equal to hn of alpha c. So integrating these is fairly straightforward. We just have a bunch of constants. All the quantities are constants over our entire integration range, so they just come outside. And if we simplify this, we finally have an expression for hn of alpha c. And this is in terms of the coil span, beta. And remember that beta is related to gamma by gamma plus beta equals 2 pi. So for beta is equal to 2 pi minus gamma. We can now plug this expression in to hn of alpha c in these expressions to get our value of hn of alpha. And so we finally have our expression for the H field in the air gap of our machine at all locations. We can then calculate from this the current linkage between the rotor and the stator. So if you recall, we've defined MMF as being the line integral of h dot dl. And we can calculate MMF along a portion of a path, or along a single path. It doesn't have to be along a whole entire closed loop integral. We can talk about the MMF drop or the magnetic voltage between 2 points by just integrating h dot dl. And if you remember, that whole thing has an equal sign pointing to the current enclosed, or the current linkage. So if we integrate MMF along a path, we can talk about the current linkage that is forcing flux through a path. And since in our case we're assuming that the H field is uniform along the length crossing from the rotor to the stator, we can just write the integral of hn of alpha between the rotor and the stator as simply being the air gap length times hn of alpha. And this is the current linkage at that location alpha. So the current linkage is the source term that is pushing flux from our rotor to our stator at any point, and we're calling that this capital theta of alpha. And we can note that in the simplest case of what's called a full pitch coil, our coil span is equal to 180 degrees, or it's equal to pi, and this expression simplifies down. And we can draw this graphically. So I started this by depicting this diagram up here, where we have unrolled our stator and plotted our current points or current lines at distinct angular locations. And what we're going to do now is we're going to draw on top of this the MMF, or I'm sorry, the current linkage. So we're going to redraw this, and then on top of the plot we're going to sketch the current linkage magnitude. So if we sketch our piecewise function, we see that in this region between the conductors, we're going to have a positive current linkage that's going to be beta divided by pi over zq times zqi by 2. And in the other regions, we're going to have a negative gamma divided by pi times zqi by 2. And as I've sketched this right now, because beta is so much larger than gamma, we're going to have a much larger current linkage in the narrow portion of the coil. So if I had made my coil a full pitch coil, so that gamma equals pi and beta equals pi, the magnitude of the current linkage would be the same at all locations. It would just switch directions. But because the coil is short pitched in this case, gamma is much less than pi, now all of a sudden in this region right here we say we have a much larger current linkage magnitude than we have over here. And we can note that every time we encounter a conductor, we have a step change in the current linkage of ZQI. So when we encounter a current going into the page, our current linkage increases by ZQI, and when we encounter a conductor coming out of the page, our current linkage decreases by ZQI. And you can verify these directions by using the right-hand rule and noting the direction of the current and what you'd expect the field path around that conductor to be. It's a little bit tricky, so first start by thinking about the right-hand rule in reference to your motor cross section up here, and then think about how that translates to your diagram, your linear diagram. Another thing to notice from this diagram is that the integral of our current linkage from 0 to 2 pi equals 0. In fact, this has to be true. That's what's left from our property that the divergence of B is 0. So remember, we were enforcing, when we calculated our magnetic field intensity, when we calculated our H field, we were enforcing that H of alpha from 0, the integral of H of alpha from 0 to 2 pi equals 0. And we can express H of alpha with all these assumptions as just being our current linkage divided by our air gap length. So this means that this integral has to be 0. And since the air gap length is a constant, that's enforcing this to be true. Let's make a few notes now. Detailed conclusions based on what we have developed so far. The first is that windings consist of coils that are connected together. The coil is a fundamental building block of our winding. And a coil consists of two coil sides. And what we have analyzed in this video so far is the current linkage of a single coil. So if we have multiple coils connected together in some arrangement, we can figure out what the total current linkage of the winding is by adding the current linkage of each of those coils. So the coil is a fundamental building block, and we have derived the current linkage of that building block and shown how we can draw it graphically over here. This is an important result, and it's something that you'll be using a lot. And so we can say that our total current linkage of a winding is the summation of the current linkage of each of these coils. And this whole game of calculating current linkages is really just a convenient way to calculate our H field in the air gap, which is just another convenient way of calculating our magnetic field in the air gap. So we like to talk about current linkage because this is kind of general quantity. We didn't have to know what our air gap was to determine what our current linkage is. All we needed to know were the physical properties of that coil, how many turns it had, and what its coil span was, and then of course where the coil was located. Whereas our expression for the H field depended on the air gap of the machine. It has this air gap length in it. And so we like to talk about current linkage because it's more general in a sense. It's independent of how long our air gap is. And so given a set of coils, we can determine our current linkage either graphically by superimposing these diagrams, or we can determine it using an equation, superimposing these equations, summing up all of the current linkages of each coil. And at the end of this video, I'm going to show you a set of rules for determining the current linkage graphically without having to go back to the equations. And the real punchline here is that if you know your current linkage, you can calculate your H field by just dividing it by the air gap length. And so this is absolutely true for when your air gap length is constant, because we proved it. And if you have your H field, then of course you can get your magnetic field. In your air gap, it's just going to be mu naught times H. And remember, your magnetic field is your actual physical quantity in the system. And in your other coursework, and as well in papers that you read, you'll come across something called a winding function. Winding function is just your current linkage divided by the current in the coils. So that's a step further generalized. Current linkage depended on current. We have the coil current here. Well, if you divide out that coil current, now you have what's called the winding function of the winding. So we said that this is true. Everything here is true for when our air gap length is constant. The question arises, what about when your air gap length is not constant? That is, your air gap length varies as a function of alpha. Examples of this include salient pole rotors, salient pole wound field rotors, reluctance rotors. It also includes when your rotor is eccentric, when it's pushed to one side in the air gap. And to handle this, you can read about this in papers. It's something called a modified winding function theory. And the modified winding function theory can be interpreted in our language that we've been developing in this video as taking the current linkage that we've derived in this video and then adding a new term to it. And this new term depends only on the coil span and the position of the rotor. It does not depend on alpha. That means it's applied everywhere. And people will call this a modified rotor voltage. It arises because of the need to enforce that the divergence of B is 0, combined with wanting to maintain this handy relationship here that our H field is equal to current linkage divided by our air gap length. And I don't want you to worry about this for now. For all the machines that we're going to be talking about in the near future, this term, this theta 0, is equal to 0. Even if I give you a salient pole rotor, it will be equal to 0. Okay, so the bottom line is that if somebody gives you current linkage, you can tell them what the H field will be in the air gap if you know the air gap length. So if you have the case that the air gap length varies with space, you're just going to divide your current linkage at any location by the air gap length at that location, and you'll come up with the H field. The final comment is that our current linkage is periodic, about one revolution of the stator. So you're traversing, you have a cylinder, so as you travel around here, as alpha goes from 0 to 2 pi, you have some periodicity. By its very nature, it has to repeat when you get to 2 pi radians past where you started. So you can use Fourier series techniques to decompose this into its harmonic content. And we'll be doing this. We'll talk about components at different harmonics, and it's going to be a useful tool to be able to talk about any given individual harmonic and either enhancing it or suppressing it or looking at the implications that it causes. And so in this video, we're talking about things as square waves being on or off, basically. You're either high up here or you're low down here. But you can also visualize this, of course, as a series of sinusoids. You've got sinusoids of different frequency components, and that's the Fourier series technique. All right, finally I said that we're going to talk about some rules for drawing these graphically. If you're given some stator, you're going to go and plot your current points on an unrolled stator geometry. And then you're just going to start sketching. You're going to start at some point, and you're going to notice that as you traverse left to right, when you hit a conductor that's going into the page, your waveform is going to increase by the number of ampere turns that are in that conductor, and then they'll level off. And then when you hit a conductor going into the page, or coming out of the page, you're going to decrease by the number of ampere turns in that conductor. And you're going to draw this waveform, and then your job is to enforce this condition here. You have to make sure that theta of alpha, the integral of theta, the integral of your current linkage over 0 to 2 pi equals 0. And that's how you'll determine your magnitude. That is how you'll determine the level at the top and the bottom. Okay, so first you unroll your stator into a linear plot, and you mark the location and direction of conductors. So we've already done this on this plot to the left. I hope you can see I've got X's here, here's a dot, here's another X, here's a dot. And I'm going to start drawing a line from left to right, and as soon as I get to a conductor going into the page, I take a step increase of ZQi, And then I resume going left to right, and now I get to a conductor coming out of the page. I take a step decrease, and here we got another conductor going in, so we take a step increase, and we repeat this until we get all the way through. And then what you're going to do is you're going to add a DC offset. You have to add an offset until the integral of theta of alpha equals 0. And to actually work this example through, I'd have to define the angle location of these conductors, and then you could iterate on it until you figure out what the amplitude or what the DC offset should be. We'll save that for another example. So to summarize here, we have developed the current linkage approach to calculating air gap normal magnetic fields. And this is an alternate approach to magnetic equivalent circuits. It gives you less details, but it is nice for studying motor windings because you have a fundamental building block approach where you've abstracted your winding away from your geometry of your motor. You can actually follow the simple set of rules we talked about, either using equations like we've set up here, or the graphical technique to construct the current linkage of each coil and sum up the results in order to obtain the total current linkage of the winding. Once you have the current linkage of your winding, you can figure out your fields and your air gap by dividing by the air gap length. And experienced motor designers will look at a winding, you give them the number of slots, poles, and phases, and they will immediately know whether this is a good current linkage or not, whether the winding has a good current linkage or not, independent of what kind of motor you have, independent of what the motor geometry looks like, just as properties of the winding. And this relates to winding factors, which we'll be talking about later in the course. We then defined some supplementary definitions, this winding function and modified winding function that you'll hear in other courses and in reading papers. And we've set up a set of rules for drawing current linkage plots.